Good morning. I'm sure you've all been seeing a lot about mixed reality today, especially if you've gone to the expo floor. You see mixed reality kiosks all over the place. So perhaps you're wondering how to get started with mixed reality, or perhaps you're already developing mixed reality apps and you're wondering about ways you can take better advantage of what tools are available for you. My name is Peter Fries, and I'm part of the XR team at Unity. And for us, we use the umbrella term XR to indicate mixed reality, virtual reality, augmented reality. And for us, the X is not just a mutable term for a letter that changes, but it's part of our commitment to cross-platform technology. So the way I'm going to do this talk today, I'm going to assume that some of you may be new to Unity or mixed reality. So I'm going to have a brief introduction to what Unity is. And then I'm going to dive into some specific topics that I think are pertinent to developers who are making mixed reality applications. And I'm going to cover some of the newer features in Unity, and then I'm going to come up with some recommendations for developers that will make their lives a little bit easier. What is Unity? So if you go to the Unity website, you'll see like these fancy terms that like the world's leading interactive content development platform. So that sounds like a lot of buzzwords, but what does it mean? I'm going to break that down bit by bit. In the past, we used to describe Unity as a cross-platform game engine. I imagine most of you aren't game developers in here. So why are we here? Well, developers used to use Unity to create games, 3D and 2D content made interactive with scripts written primarily in C#. But along the way, we've evolved into something much bigger. We certainly still support games, and games have very specific real-time interaction and rendering requirements. But Unity is now used for a wide range of non-gaming markets. And they all use Unity because they are creating applications that have those same real-time interaction and rendering requirements. Earlier part of that phrase is world's leading. Well, that's not hyperbole. Unity's development platform has massive reach, running on nearly 3 billion devices, and it's the tool of choice for VR and AR development. Just last year alone, Unity had unique downloads of Unity apps of 24 billion downloads. So still, what is Unity? To some developers, Unity looks like this. It's an integrated environment, allows you to create complex and interactive 3D content. You attach components which provide functionality to objects. And the components can define everything from how the object renders to how it behaves with things like physics. But to other developers, Unity looks like this. It's a fully scriptable engine using C# and features a rich API that allows you to manipulate objects and interact with services. Nearly every platform you can think of, Unity is on it. Desktop, mobile, console, and VR and AR. We currently support 25 different platforms, and this number is definitely growing. And we work alongside large partners like Microsoft, Google, Facebook, and Apple to ensure optimized support for all their latest hardware. Unity is driven by 3 core principles: the desire to democratize development, to help in solving hard problems, and to enable success. We work towards all of these with our support for VR and AR. The Unity editor's rapid iteration makes new development easy and accessible. Our highly optimized rendering pipeline can help you achieve exceptional frame rates. With Unity, you can create XR applications that run on multiple devices without having to learn a new API. And Unity has been there from the beginning with Windows Mixed Reality. We started 2 years ago adding support for HoloLens early in development, and we had something called a HoloLens technical preview, which was available to early developers. And we did the same thing with Windows Mixed Reality. We've been supporting HoloLens officially since 2016, and we added official support into the Unity mainline for Windows Mixed Reality on desktop last year. So I want to talk about how easy it is to take an application that's already written in Unity and enable VR in it. And essentially, it's one click. This is part of what we believe is solving hard problems. There's a lot of things that happen under the covers with that one click, but essentially, you simply enable VR in your application, and the application runs on VR. Now, there's more complexity to that, but this is all it takes to get you up and rendering for Windows Mixed Reality. And to demo that, I'm just going to show you how easy it is. And So let's see how I do with a live demo of this. All right, so I've got a simple application here. It's just an object that has a simple script attached to it. And if I hit play, oops, I may have anticipated things. All right, so we'll just jump to the end result. So this is, if I can find my cursor, this is that checkbox you just saw on that screen. This is virtual reality support. So if I turn this off and hit play, we'll just be running in the editor. I'll drag the window over. And so there's a simple object animating. This is an incredibly simple, this is a programmer project, no artists involved. So I'm going to hit stop, and I'm going to go back over here, and I'm going to turn on VR. Now, as soon as I do this, I get a little drop down of the virtual reality SDKs that are supported. Since I've selected a Windows UWP as my target, I only have one API available, which is Windows Mixed Reality. If I was targeting some other platform, I'd have access to other APIs. You could target Oculus, Vive, ARKit, ARCore, those kind of things. So, and over here, this is the, I've got a Windows Mixed Reality headset running, and I'm running it in the shell right now. So I'm going to tab back and run that same application. And basically, I've just launched a mixed reality app from Unity. Where's my app? There's my object. It's underneath me. So I hope you can see that. So anyway, that's all I had to do to enable mixed reality in a Unity application. Switch back. So that's great if you're developing on desktop. And what if you're developing on HoloLens? Well, if you're developing on HoloLens, things are a little different. It's, the desktop application is actually running on the same desktop computer that you're running the editor in. The HoloLens is a standalone computing device. So normally, the process would be test in the editor, perhaps using some subset of the APIs, and then you would deploy to the device, and that involves creating a Visual Studio solution that you then build and then deploy to the device. So the iteration time can be several minutes. And we wanted a way to improve that. So last year, we added a feature called holographic emulation. And we have two modes we can run this in. One is holographic remoting. And this allows us to connect to a remoting player on the HoloLens and still gives us the ability to still run the device in the editor. So this is awesome for iteration time. It means you can test your app, iterate, make changes to the application, make changes to your script, and you don't have this long development time. So incredibly powerful for developers. The other option is something called simulation, which allows you to, even if you don't have a HoloLens device, you can run on a virtual machine HoloLens directly from inside the editor. So even developers who don't have access to a HoloLens, or perhaps someone else in your team is using the HoloLens device because you have limited numbers, you can still work on your application. So anyway, as I said, this is pretty awesome for developers, rapid iteration. You get actually what's rendering on from the editor is exactly what's rendering on the HoloLens. So there's no fakery there. Most of the API is supported. So with the HoloLens, that means you have access to the hand gestures, and those will actually be transmitted across the network to the Unity editor. You have access to spatial mapping, so you can read in surface data from your environment and have your application reason from that data. The only limitation is currently right now, speech input from the HoloLens is not supported, and also the photo and video capture from the HoloLens will actually use the photo and video capture from your desktop machine. And if you've done any HoloLens development, you may know about world anchors. Those are currently not supported. We're not sure if we'll be able to add support for that. There's some interesting network burden that happens because of the size of the data set. So the HoloLens is a pretty powerful computer, but sometimes you want more for your standalone applications. So the CPU is a 1 gigahertz processor, Atom X5. You've got 2 gigabytes of RAM. And if you've already done HoloLens development, you know you have to really trim down what your application can do to get it to perform well in the HoloLens. So achieving high frame rate is really important for any sort of immersive environment. So what if you wanted to take advantage of the type of remoting I just showed you, or I indicated you could do from the editor? I actually have a demo that I can't get working right now, so I'm going to talk over that. But I've got some videos to show you of some interesting things. But what if you wanted to be able to take advantage of the same sort of connectivity you get of connecting to the HoloLens from the editor and running your application from your standalone application? In other words, what if you wanted to use the full power of a desktop computer on the HoloLens? So in 2018.2 of Unity, we're allowing you to do just that. You can create a standalone remoting application. So this is going to connect to the HoloLens. The application will run on a full-powered desktop computer, connect to the HoloLens over a network connection. The user or users wearing the HoloLens will see the full rendering environment, and you get the power of the desktop on the HoloLens. So I want to show you two examples of some companies from very different industries who are already using this standalone remoting to create applications, which were not previously possible. The first one is MetaViz. So MetaViz is a technology company that was created to leverage augmented reality and artificial intelligence to transform medical and surgical visualization. So medicine has traditionally used 2D grayscale images to understand complex 3D anatomy. The first CT scan was done nearly 50 years ago, but today we still show grayscale images. The resolution is higher, but there's no better way to visualize the data. So medical imaging often creates very large 3D textures, 512 by 512 by 512 volumetric textures. This is far beyond the RAM capabilities of the HoloLens. So they were able to use standalone remoting to allow them to offer full resolution versions of this volumetric data by running the rendering on a desktop computer. What you're seeing here is their RenderX software running in an operating room. This is all captured directly through the HoloLens. And this is allowing doctors to have surgical visualization through reconstruction of traditional medical imaging data. So this is pretty awesome, and like this could potentially transform medicine. Another early adopter of this technology is Volkswagen virtual engineering team in Wolfsburg, Germany. So they've used augmented reality to help save time and development costs. They have tools that allow Volkswagen engineers to work on a virtual vehicle, to change its equipment as they wish, and even design new components virtually. They can be able to see the results of their work immediately. Now, the complexity of CAD models that they're using can contain tens of millions of triangles. This geometric complexity is beyond the capabilities of the current HoloLens. So they were able to use standalone remoting to be able to show these full resolution models directly on the HoloLens device and using high quality shaders. I should mention that Unity is now partnering with Pixies, which is a CAD software technology company. And if you visit the Unity booth, you can find out a little bit more about how you can directly use CAD data inside Unity. So this is where I do my remoting demo. So actually, I'll do this demo, and I'll do it with mixed reality hardware. So I want you to imagine I'm showing this on a HoloLens. One of the issues with the HoloLens that is difficult to demo in a room like this is I have to have a Wi-Fi connection to it, and you're all using the Wi-Fi as well. So it makes the connection a little bit unstable. So I'm just going to demo this with the same mixed reality hardware. But I want you to imagine that this is running on a HoloLens, and think about how you could take advantage of this type of rendering capability on a HoloLens. So I've got that same model, which I don't remember how many triangles it was. So it's just some CG, like very simple CG constructed geometry that I'm animating, and I have some simple, not terribly simple, but photorealistic shaders on it. But instead of rendering one of them, I'm going to render 10,000 of them, which gives me a triangle load of about 15 million triangles. And so here's that same scene, and basically I'm running a full, like I'm basically running at 90 frames per second right now. So, and this is essentially the same view I would see on a HoloLens. So So I want to talk a little bit about stereo rendering right now. So in a traditional rendering environment, we render the scene from a single view. We take the objects in the scene, we have geometry associated with those objects, and we transform them into a space appropriate for rendering. We do this by applying a series of mathematical transformations to the objects, where we take them from a locally defined space into a space we can draw on the screen. This series of transformations is sometimes referred to as the graphics transformation pipeline, and it's an essential part of classic technique and rendering. So VR devices introduce the requirement of defining two views to provide the stereoscopic 3D effect that creates depth for the viewer. So each view represents an eye. And while the eyes are viewing the same scene from a similar vantage point, each view possesses a unique view and projection matrix, and they may even see the object slightly different because of lighting calculations. In order to render the view for each eye, the simplest method is to run the render loop twice. Each eye will configure and run through its own iteration of the render loop, and at the end of the process, we'll have two images that we can submit to the display device. And what you're seeing right now is how what we call multi-pass rendering works in Unity. We render all the left eye, and then we render the right eye, and then we combine those into a single unified view. There are some performance implications of this. And so last year we looked at ways to improve this, and we came up with two techniques. And in 2017.2 last year, we released support for something called stereo instance rendering. And this works for all XR devices running on DX11. So if you're running a Windows mixed reality device, it's definitely on DX11 because that's required for support of it. So this is some extensions of some work we did previously to support single pass stereo on other types of devices. And those we used a double wide texture. The way single pass instance rendering works is we use instead of two separate textures or a double wide texture, we use a DX11 texture array, and we're able to multiplex the draw calls using the GPU, some of the GPU extensions in DX11. And essentially, we do two things. Instead of rendering through our whole scene graph twice, we only have to traverse the scene graph once. And the other advantage we get is instead of issuing two draw calls, one for the left eye and one for the right eye, we issue a single draw call, and then we allow the graphics processor to split those across both eyes. So this halves the number of draw calls required, and that's a performance gain. So to enable single pass instance rendering in Unity, it's just as easy as enabling a checkbox. So I should point out that we default to multi-pass right now because some applications may have custom written shaders and they don't implicitly work on single pass instance stereo rendering. So there's some shader changes that you might have to make. So this is an idea of what some of the performance differences are. And you can see that most of the performance gains are in the CPU, not on the GPU. The graphics processor is already sort of working at full efficiency regardless of how we do it. And we find that a lot of mixed reality apps end up being CPU bound. So this is a huge performance gain for them. The interesting thing is, if you start out CPU bound and you make some optimizations, then you find you're GPU bound. And so it's a little bit of a ping pong back and forth to try and make your performance go up. But you'll notice that one of the things on here is the single pass stereo and single pass instance stereo aren't as significant gains. And we think the reason for that is a lot of graphics drivers are already multi-threaded, so they can split up some of this work. But in either case, it's a pretty significant performance gain. So this is a little bit of the more technical parts of my talk. If you do have shaders, custom shaders that you've written, and you're looking to take advantage of single pass instance rendering, there's a couple changes you'll need to make to your shaders. The simplest one is just turn on the instancing for your materials in Unity. And then we have a bunch of macros that you'd want to use in your shaders to help make support for single pass instance rendering easier. Your vertex shader will need to have an additional output parameter that'll specify which index of the texture array is being used. And so macros will do that for you. And if you have any screen space or post-processing shaders, they'll also need to do some special things because you can't simply assume that the UV coordinates that you'd normally deal with are the correct ones when we're doing stereo instance rendering. As I said, one of the core principles of Unity is solving hard problems, and we try to do that with VR. So as I showed you in a demo, converting an existing application into VR easy as ticking a checkbox. Well, that's not really true. There's a bunch of more things you have to do to make your application really a VR application. And dealing with input is another one of those. So what happens when you enable that? One of the things that happens when you enable that checkbox is that Unity, when you run your application, Unity finds the main camera in your scene. Now, simple demo applications will only have a single camera, but sometimes you'll have multiple cameras in the scene. So we try to figure out which one is the main camera intended for the HMD, and then we control that camera via input from the HMD head-mounted device. So this is the way that VR has worked in Unity since we had support for it several years ago. But this required developers to add their own support for handling controllers. So we wanted to create a system that worked for controllers as well as the head-mounted devices. Last year, we added a new component in Unity called the track pose driver. So this works for the head-mounted devices as well as controllers. And you can use it to define various types of ways you're going to drive the camera pose from the head-mounted device. You can have it track with the left eye, the right eye, a center eye, or the middle of the head position. And you can specify if you're driving controllers with it, whether it's the left controller or right controller. And there's a couple ways we're going to extend this for other types of input devices. So this will, if this is enabled on a game object, it replaces the implicit camera update that happens by default. Now, if you think about this, one of the things that can happen in Unity is the camera position is controllable in the editor. So you can start out at, it can start out at a 0, 0, 0 position, but developers and content creators can move the camera around to get a view of the scene. So what happens with that if the headset is controlling the position of the camera? And the way we made this work is that we capture this transformation that's on the camera initially. We call that a reference transform. And then whenever we read input from the headset, we post-apply the transformation of that camera so that the headset matches what the expectation is of where the camera was initially set in the scene. So this sounds a little complicated, and it can actually lead to problems for developers because there's some confusion around this. One of the issues is this only applies to that node. So if you have other nodes in your scene graph that you want to control, say, controllers, they can be in a different reference frame than the headset. So you're running your application, and your controllers are 5 meters over to the right. Why is that? So this kind of has led to some problems for developers. And so we actually have a recommendation of how to set up a scene graph using some VR components that I want to show you now that I think will avoid some of that confusion. And we're actually going to be discouraging people from using that implicit reference transform. And that's why, let's see on this other slide here, this is a checkbox here that just sort of says enable that reference transform. And we're going to be probably deprecating this at some point in the future just because we think it adds complexity and we think there's a better way of doing this. So this is a kind of how we imagine, this is a very simplified view. Obviously, your scenes would be much more complicated. But this is the basic essence of how we imagine you would want to set up what we're calling an XR rig. So you have some root node. And this is the thing that you want to move the player or viewer. I call it player because that's the way Unity refers to things. Our background is a game engine. But the user, this is what you use to move them around the scene. Now, obviously, if they're wearing a headset, a HoloLens, or a mixed reality device, they can move, but they're going to have limited movement. And one of the things particularly if it's a mixed reality headset where they're tethered to a computer, they want to explore different areas of the scene. So you're going to need to have some sort of way of teleporting them around the scene. So this would be the node you would use to do that. So you have complete control over where this position is. And we also recommend you use this to represent their position at ground height. Beneath that, you have a child node, which we call the floor offset. So there are a couple different ways of dealing with coordinate systems in mixed reality. And some of them depend on which type of device you're using. If you're using a HoloLens, everything is going to be what we call world tracking. So the device, when you first turn it on, its current position is going to be considered 0, 0, 0. And whichever way it's looking, sort of the yaw, that's going to be the orientation, not accounting for pitch and roll. But with the desktop immersive devices, they can act that way as well. But they can also act as a coordinate system within a reference frame that they specify when they do the setup. And this is if you do your initial configuration, you set up a boundary for the device. In that case, the coordinate system will be 0, 0, 0 is the ground at the center of that boundary area. So Unity supports both of these, and we'll implicitly choose the best one for the device. But this is what this node is for. So if your application needs to run on HoloLens and a mixed reality device, or you're running on an immersive device and you don't know if the user has set up a reference frame, this will allow you to deal with that floor offset either way. And then finally, we have nodes for the camera and any controllers. And you can just add the track pose driver on these and use these to drive the headset position and the hand position. So that gives you input about where the headset is and where the controllers are. But you need to do more with input than that. You're going to want to be able to use the buttons on the controllers as well as potentially give haptic feedback to users. So you can't do that through the track pose driver. And there's two different ways of doing this in Unity. So there's sort of the cross-platform way, and then there's a Windows mixed reality specific way. And there's advantages and disadvantages to each. So using the cross-platform way is use the existing Unity input system, and you've got just some APIs like get input, get access. This will work across any type of device, any type of controller. The downside of these is you have to kind of look up what the button mappings are and what the access mappings are. These are all documented, and I'll give you some links at the end of this talk where you can find those. But there's also some interfaces we provide inside the Unity WSA input namespace. And these give you much more control and more specific input from the devices. So you can access any of the buttons exposed on the controllers, not just a few of them. And you also get access to the gesture recognizer, which is an important interface API for the HoloLens. So this is one of the interfaces inside the XR WSA namespace. And this is the interaction manager. So you have two ways of dealing with this as well. So you can use a polling method where applications will query each frame and find out what the state of the devices are. Now when you do polling, this will actually give you forward predicted pose information for controllers and the head. So you want to know the state of the controller, you can poll it, and you can find out what buttons are down, and you can find out the position of that controller in space. But what I mean by forward prediction is one of the hard problems in VR is latency. So you have the computer application running and rendering the objects in the scene, and then at some point it appears on the headset. And the latency for that whole process can be 30 to 40 milliseconds. And if we don't adjust and account for that latency, the experience is really bad for the user. So there's a bunch of prediction that goes on. So then when the scene renders, it'll actually render what the predicted headset position is. And then at the last moment, there's also a fix-up based on corrections to that prediction. So when you use this polling interface, this will actually give you forward predicted pose information based on the controller's current position and their velocity. And using this API, you can find out whether touch or menu or select or thumbstick. Here's one of the joysticks if you haven't seen it, so you can find out the state of all these interfaces on this. There's also an event-driven interface. And this will give you information about the source and head pose, but not forward predicted, but when the event occurred. So this is important for handling the intent of user because it uses the state of the controller and the hand at the time the event happened. So we have event handlers for detected, lost, released, and updated events. So the pressed and released events are always going to be bracketed somewhere within a detected and lost event. So when the headset sees the controller, it'll do a detected, and when it's out of sight, it'll be lost. The same is true on the HoloLens. When the hands are visible, you'll have a detected event for the hand and a lost event when the hand is no longer visible. The next topic is a little interesting. So when we started out with Unity, we originally had 3 different scripting languages: C#, something called Boo, and something called UnityScript. And UnityScript, that was a JavaScript-like language. And to make things, our lives are much more sane now because we only support a single scripting language, which is C#. Developers seem to prefer this. It's much more powerful and allows better application sharing. And we use the Mono compiler and the Mono backend to support C#. When we first added support for Windows 8 Store apps, though, we couldn't use the Mono runtime. Windows 8 Store already had a .NET backend, but there were some API limitations that we were not quite able to get around. So things like suspend thread, get thread context, virtual alloc, these weren't available to us for applications. And so what we ended up doing was we ported Unity to .NET. This is a tremendous amount of effort on our part. It's something like 500,000 lines of code to make all this work. And there's a couple issues with this. There's a slightly different API surface than .NET 3.5 on other platforms. And any developers who have an application that works on some other platform through Unity, and then they port to UWP, this is going to be a significant porting pain, because they may find some of the APIs they're using don't exist, or they're slightly different. Our asset garbage collection had to be written for .NET, and some features we actually couldn't implement at all, so it was end up being a subset. And this is still a lot of resources to maintain. So 2 years ago, we introduced something called IL to CPP. This was actually for other platforms other than UWP, where we didn't have access to any .NET, and we couldn't use Mono. So what IL to CPP, it's a Unity-developed .NET runtime. So we compile the C# code using Mono or some other C# compiler. And then IL to CPP converts the IL code into C++ code. And then we compile the C++ code into whatever native binary files, whether it's an exe, an APK, an XAP, whatever, for the specific platform you're working on. So the biggest advantage of IL to CPP is that you can create scripts which compile across all platforms without any modification. It's the same .NET backend. This gives us the ability to have a robust, performant, and consistent API surface across platforms. There are a couple limitations right now that we're fixing very soon. The first is that there's currently no managed C# debugger for IL to CPP code. So if you're building a project using IL to CPP and you want to debug it, you're going to be debugging the C++ code that's developed. That can be kind of difficult. We have some blog posts that describe how to do that a little easier. But we're actually fixing this in Unity 2018.2, which we'll be releasing later this year. And it's in beta right now, so we've already got this working. So this is going to be integrated with Visual Studio 2017, Visual Studio tools for Unity. And we're also going to make this work with JetBrains Writer. So the idea is you can build your code, write your code in C#, compile it, it'll run through IL to CPP automatically. But then when you're debugging your application, you'll actually be able to set breakpoints in your C# code and step through the code just as you would with the .NET backend. The other issue is the full builds are slower and iterations a little bit more cumbersome, since any code changes are going to have to require recompiling the C++ code. And as of 2018.2, full incremental builds should work with that. And I also recommend, if you're doing this, just run your builds on an SSD and make sure you don't have anything like malware scans going on in that drive. So that'll improve the performance. And the other thing you can do is you can just do your iteration directly in the editor, which I showed you. It gives you full access to the device and all the controller input. So if you want to enable IL to CPP, basically you just go through, and in the project settings that you can see right here, there is a scripting runtime, and you can change that to IL to CPP. And if you want to use some of the WinRT API functions, just set your API compatibility level to .NET 4.6. Now, if you've got some other APIs that you're using from other vendors, you can just take the WMD files and drop those into Unity, into your project, along with the DLLs, and then you can call those as well. So we're going to be encouraging developers to use IL to CPP. Sometime later this year, we're probably going to be deprecating support for the .NET backend in favor of IL to CPP. So IL to CPP is something we really want to get right. So I encourage everyone, if you're doing stuff in Unity, take a look at it. Please give us feedback. We're really committing to making IL to CPP excellent. The .NET support that's in Unity 2017.4, we're going to continue to support that for at least 2 years. So you're not, .NET backend is not going away magically. You have plenty of time to look and do the transition to IL to CPP. So at this point, I want to give you just some really simple guidance if you're doing Windows Mixed Reality development, some tips that I think will make your life a bit easier. The first is to take a look at IL to CPP, which I just talked about. It's available now. And if you have any feedback, please give it to us. We really want to make this excellent, and we're committing to supporting this. And also, don't use that implicit reference transform on the camera. That's going to make synchronizing with controller input more difficult, and your life will be a lot easier if you just keep that camera zeroed out and handle moving the user around the scene via a higher level node in the scene graph. So this one is interesting. So if you're debugging and you hit a breakpoint and you're running in full screen, you'll basically just see this UWP tile filling your window, and you won't see Visual Studio in the background. So you may be confused what's going on. There's really no reason to have full screen enabled for a mixed reality immersive app. All that really does is just set some initial settings on the windows. And because of the way Unity works, it's kind of hard for us to make that not work for UWP apps. So I just recommend turning off the full screen by default. There's no real reason for it to have that enabled, and it'll make development for mixed reality a little bit easier. The second thing related to that is also a debugging thing. Right now, the way Unity detects when the user is wearing the headset is we actually check for window focus from the mixed reality core window that's associated with the headset from the OS level. And so when you take off the headset, that window loses focus. So the same thing can happen if you actually tab out to another application, like Visual Studio. So if you're debugging an application, you hit a breakpoint, essentially from the mixed reality application, it says, hey, some other app has focus. I need to stop rendering. And so it'll pause rendering, which makes your application go, am I rendering or not? So there's a toggle you can just set, which enables you to always continue running in background, regardless of whether the app has focus. Now, that may not be what you want to ship with, but it'll make debugging a lot easier. And I also recommend use single pass instance stereo rendering. Unless you have some custom shader that you can't adapt, this is basically a free performance gain for you. And so this other one is a little tricky. I want to explain this briefly. So Windows Mixed Reality uses a process they call late stage reprojection to compensate for movement of the user's head between the time a frame is processed and when it's rendered and when it appears on the display. We usually call that the time to photon, which is when your photons hit your retina. And so to compensate for this latency, there's a couple things that happen. First of all, as I mentioned, there's this prediction that we use, which says, based on where the headset is now and based on its current velocity, and we know about how long it's going to take to render this frame, we can predict where the headset will be. And so we'll render the scene from that future predicted point of view. But there's a little bit more that goes on, because when the device actually does composition of the scene onto the headset, it does this additional process called late stage reprojection. So it takes where it thought the headset was going to be and where the headset actually is, and then it'll adjust the image by reprojecting it onto the display to correct for that error between the prediction and reality. On the HoloLens, this reprojection is done using what they call a focal plane. But desktop applications can actually get better quality rendering by using per pixel reprojection. And to enable this, there's this little flag which says do depth buffer sharing. This basically gives the Windows Mixed Reality runtime access to depth information as we share it. So it can take a look at each pixel, know its depth in the scene, and do correct reprojection for that. So enable this for desktop applications, and you'll get better reprojection. On the HoloLens, what the depth buffer sharing will do is actually give the device API a little better sense of where the average holograms are from the user. And so reprojection will happen on a plane level, but you don't have to set that plane manually. Unity does have APIs to set that plane manually, but this is a much easier way to deal with that. And if you're developing on HoloLens, there's a couple considerations you want to give to performance. And I'd recommend you setting in the Unity quality settings, setting the fastest quality settings for the HoloLens. So this will maximize performance and reduce power consumption. In particular, you want to avoid things like soft shadows and using shadow cascades. They require a lot of resources from the hardware, and they're not really necessary for the type of rendering one would do on a HoloLens. So I talked about remoting earlier, but there's an additional, I mentioned this briefly. So inside the Unity editor in the holographic emulation window, you can change the type of emulation from remoting to something called simulation. This is basically a built-in HoloLens simulator in the editor. So this will give you access to everything that you would normally have on the HoloLens. The way you do it is you enable it inside the editor, and you can drive a virtual human around with which I don't have a controller here, but anyway, like an Xbox controller. So you can drive the human around, and you can simulate the hand positions using the controller. So you can completely create your HoloLens application without having a physical HoloLens. Obviously, you want to develop at some point on that before you ship a HoloLens application. But this is a tremendous aid for iteration. And you can even load virtual room information using this. So you can specify a couple different room environments, so you'll have access to spatial data as well. And if you're developing desktop mixed reality applications, you can also do this without physical hardware. There's a simulator built right into the mixed reality portal. So if you open up the mixed reality portal, on the left side, there's a little developer button, and you can simulate the headset and simulate controllers that way. And you can drive the virtual human around inside the mixed reality portal using the keyboard and mouse. So it's WASD keys and the mouse for steering. And also, I mentioned the interaction manager for accessing input. And there's a little tip I want to mention. So if you're reading mixed reality input using interaction manager, particularly on HoloLens, there's one of the source parameters is something called handedness. So you can tell whether it's a left or right hand. So if you're working on HoloLens, that will always report unknown. This is just the Windows API doesn't give us the information for hands. If you're working with these controllers, you will actually get left and right because these can distinguish. But if you're doing an application that might work on either, I would recommend not using the hand information to correlate events. So if you get a pressed and released event, don't correlate those by the hand information. Each of these events will actually have an ID associated with it. That ID is guaranteed not to change. In the latest version of Unity, if you're using a HoloLens, we'll actually synthesize hand information based on where we detect the hand, but that the reasoning based on reasoning to figure out which hand is visible can actually change as we update our knowledge about the state of things. So if you see this hand, we go, or if you started over here and we go, we think that's the left hand, and then we do this, we go, ah, that's the left hand, so this is actually the right hand. So the reasoning can change. So always use the source IDs to correlate events. So you've heard me talk about like 2017.2 and 2018. I want to explain a little bit about how Unity releases updates. So earlier this year, we've sort of changed the way we do updates. We used to have a very traditional version models, and users would pay for each version. And last year, we switched to a subscription model, and we've changed our release model a little bit, and I think in a way that will better service developers who want to have either A, the latest features, or B, a very reliable, robust version of Unity. So we have two development streams, what we call the tech stream and the long-term support stream. So right now, we're in the 2018 tech stream. This is where we introduce new features. Last year's version, 2017, is what we're calling our long-term support stream. So we do three iterations per year, a 0.1, a 0.2, and a 0.3, and then the last one becomes what we call our long-term support stream. And this is a version or a branch of Unity where the only changes we make to it are bug fixes. We don't introduce any new features which would destabilize it. So you can either have the very robust version that doesn't have new features or new features. So you're probably wondering, well, I don't know, which one should I get? And the answer is get them all, because we introduced something called the Unity Hub. And this is an awesome tool. It's a front end for Unity. And you can actually choose which versions of Unity to install, and you can sort of experiment with tech release features and then go back to working on the LTS stream. So this is kind of cool. I just tested this out last week, and I had to download 3 different versions of Unity. So click download, 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 go and get a cup of coffee, and I come back, and they're all set up on my machine. So that's really awesome. And this will basically let you see when new versions are available. And you can even choose to launch a project with a particular version from the hub. Yes? Yep. The question was, is this available? And it's available now. And I'll have a link later on to how to get this. The other thing we're doing this year into our tech stream is we're introducing a package model for how we release features to the tech stream. So in the past, it's one of the problems we struggled with at Unity was how to get new features available to developers as quickly as possible without destabilizing the product, but also in a way that coordinates with everything else. And because we're very concerned about testing and making sure everything works well together, our lead time for getting features available to people can be slower than we want. So what we're doing this year is we're introducing packages. So this does a couple things. First of all, the core install of Unity will become slightly smaller. So there will be some features of Unity that are now available with packages. And the way the package works is you just enable the feature that you need in your application. So additional APIs will become available. It'll download the package automatically into the editor. And we're actually going to be moving a lot of Unity features into this package model. Coming later this year, we're going to be taking our support for XR and making this a package. What this does for us is this will let us develop some of our XR features independent of the regular release cadence of Unity. So we can get new features out for testing much faster to users and also do fixes much faster. And we're actually going to be doing internally a new API that we're going to allow us to support a much broader range of devices using this package model. So this is my call to action slide. If you're not already, just check out Unity, and here's what you need to get started. So you need Visual Studio 2017. So download the Unity Hub. There's the link right there. It's Unity 3D, get Unity download, and there's a big link for the hub. It'll make installing Unity easy. And check out the Windows Mixed Reality site. There's another link there which will give you a landing page which will tell you all about Unity Mixed Reality. And if you want to learn about Pixies, go visit our booth in the expo hall at E21. There's some people there from Pixies and Unity that would love to talk to you about how to get CAD integration in Unity. And get one of these headsets. They're awesome. They're amazing. And yeah, I can't tell you how awesome it is to work with these devices. It's so cool. And finally, give us feedback. If there's anything you want to see us do or you think something we're not doing well, let us know. Particularly, as I said, we're very concerned about making IL to CPP perfect for you. I know a lot of you are very committed .NET developers and maybe find the idea of like this other backend really scary. But we want to get it right and we want to make it excellent. So we're very committed to supporting that. So at this point, I have time for a couple of questions. So I think they're recording this, so I'd recommend go using one of the microphones.
Hi. My first question is the IL2 CPP backend. Is there like a specific benefit of using it for MR development?
Yeah, so the biggest development is simply a consistent API service across multiple platforms. Now, if you say, I don't care about any other platforms, why would I want to use IL to CPP? We actually think it will be actually more robust as well, just because it's less code for us to maintain. There's also some performance gains because you're not using just-in-time compilation, but I mean, those performance gains are kind of minimal. And there's speculation that it could make your applications a little bit more secure, but you're already taking care of security through the APK. So.
Okay. And another question I had was regarding like if you use like UI Canvas, how does that like work with the headset?
Oh, right. So the question is, how does the UI Canvas? So one of the components of Unity is something called the UI Canvas, and this is a component that allows you to do UI composition. This does work with the headset. Normally, if you're creating what we call a flat desktop app, you have a way of setting up this canvas to work in screen space mode. Well, there's no screen space mode with a VR, AR device. So what you end up doing, there's an option on this where you create a world space canvas. And you basically position that canvas somewhere in your scene in 3D space. Now, it could track with the camera if you want. There's a bit of nuance to making that look right. You don't want something rigidly attached to the headset, because that actually is not a good experience for the user. But you can have it float and then kind of slowly move to follow the user. But you want to set that canvas up so it's in 3D space. So all your UI is there. So it does work, and that's how we recommend using that UI canvas with VR and AR apps.
So is it easy to like have it so that you still have that screen, the locked-in view for a traditional game, and at the same time share that code for a VR game?
So I think your question is like how would you deal with a game that is both VR and non-VR? You could do both. I think there's a lot more than simply changing the UI. Like, as I mentioned in the beginning of the talk, it's very easy to enable VR, but there's a lot of user interface considerations for making a good VR app. And it's more than just simply changing your UI from screen space into world space. There are a lot of other considerations.
Okay. And my last question is with regard to input. At least with mixed reality, it's like you get that pointer that comes out from this. Like, is that all built in, or is that something we have to calculate?
So it's not implicitly built in. If you go to the Microsoft site, Microsoft has something called the Mixed Reality Toolkit. There is a way of getting the geometry and mesh data for these controllers into something called a GLTF file that is loaded dynamically, and there's another DLL you need. There's examples of this on the Microsoft site of how to do that. So yeah, it's actually pretty easy to access, and their examples will actually animate the thumbstick. So if the user sees moves the thumbstick, this model will actually animate. And so there's other things you can do, like you can highlight things if you're doing a tutorial to tell the user, like, press this, move the joystick this way to spin the car model or something. So it's easy to do.
Yeah, I mean, my question was exactly like, if you're not like touching something directly, but like pointing to it in the distance, is that built into that interaction framework?
The interaction manager. So what you do is in this controller, there's 2 bits of pose information. There's what we call the grip pose and the pointer pose. The grip pose is sort of going to be the position of this pointer or this controller and its orientation in your hand. And the pointer pose will depend somewhat in these controllers, which are almost all the same. But if you look at this way, you see that this has this angle and this has this angle. So the pointer pose will have a different orientation. And that gives you the ability to construct an array to see what the user's pointing at.
Okay, thank you so much.
Yeah, a quick question about the remoting. What exactly is happening from the render machine? Can you talk a little bit about what's happening from the render machine back to the HoloLens in particular? Like, the calculations are being done, events are being passed, all of that, but what's happening on the return?
So right, there's a network stream set up between the 2 devices, and from the desktop machine, we're basically transmitting frame information, which is the rendered scenes, as well as some additional information, meta information about those frames, about like where they are in space and what the time sample was that they were rendered at. Back from the device, we get information from another stream coming back, and we'll get surface data coming in from the device. So you're wearing a HoloLens, you can see the triangle mesh data from the room. You'll also get hand information and head pose information. So all your input stuff is there. As I said, the thing we don't support right now is voice. We're working on making that work. So you can actually have all your input working from a HoloLens application, except voice. Right. So there's always, as you mentioned, there's latency. But we actually account for that latency. So there's latency in the time that we render the frame to when it gets transmitted over the network to when it actually gets composited on the device. Reprojection actually takes care of that latency. So the device can actually go, oh, I know the time frame that this frame was rendered for like this particular time slot. And so this is where the headset now, this is where it was, and it can correct the image. And that'll work even like if for some reason your application performs very badly and you only get 10 frames per second. The cool thing about reprojection is reprojection happens at a device refresh rate. So on the HoloLens, that's 60 frames per second where it does its own refresh. So your image is stable regardless of what your application, animation will not, if you're running animation, you're only going to get 10 frames per second of animation if that's what your app is running. But the reprojection will happen at 60 frames per second. So your images will be very solid and stable.
Yeah, hi. I have 2, I have a small remoting question and maybe a bigger remoting question. The small one being, is there a plan from you or probably more specifically Microsoft to be able to enable remoting, not over Wi-Fi, but over a wired IP over USB connection?
Yes, absolutely, and it does work. And that was part of my demo today, but I had a little problem getting it set up because I updated my HoloLens to, there's a new pre-release OS for it, so you can get RS4, Redstone 4 for the HoloLens. And so every part of my demo worked except when I tried it over the USB here, it wasn't working. So there's a few little finicky bits of it. But yes, you can actually do it over wired connection. So obviously, it requires a tether on the HoloLens.
Sure.
There's two advantages. One is you get the better bandwidth over that USB connection, and the second is you can supply power at the same point. So if you really wanted to do some custom thing for people where they were wearing HoloLens, running this application for an extended period with power, you could actually take advantage of those. But
That's only in the preview OS? For the
no. This actually works with RS1. So
Oh, okay.
yeah. So it's yeah.
Okay.
It's all working today and been working. So
Okay, yeah, 10.0.0.80, yeah, but, hadn't gotten that to work yet. Okay, next is, so you said in 2018, you can build a standalone app that can support the remoting. Unity can now build a standalone.
Exactly.
How do you do that?
let's see if I can go back in my slides really quickly and see this. Because there's a little,
I like that question.
I think I called it out. Almost there. There it is right there. So it's basically on the build settings, and this is in 2018.2 right now, so you can try this out.
Cool, thank you.
Sure.
My question's very related. I'm just wondering if I can build that standalone app for like iPhone or all of the Unity platforms, or does it have to be like desktop UWP? Like, can I make my phone be the rendering engine for holographic remoting?
Is your question in regard to remoting as a standalone? So remoting right now, this type of remoting is only available for Windows Mixed Reality, the HoloLens. There are some other ways that we support remoting, but they're intended on other devices like Android. There's an Android remoting player, but I don't know a whole lot about that. But my understanding
well, I
is
want the
those are
HoloLens to, I want to wear a HoloLens, but render on my phone.
render on what?
On my phone.
No. So the rendering has to, so the base app has to be a UWP app.
Okay, thank you.
So.
Hello, thank you for the good talk. I have a question about UI canvases.
Sure.
I'm working on a project that is doing data visualization and charts. So basically for some data it makes sense to be 2D, and we're using UI canvases. Is there any performance penalty in terms of how many UI canvases can you have on the scene in world position?
So your question is about, are there performance considerations to having multiple UI canvases?
For example, say 5 canvases, 10 canvases.
Are all these canvases present at once, or you enable and disable them?
It depends. They can be present at once within the scene.
So in order to get UI performance, to improve UI performance, the UI system does what we call batching. So it looks at all the things you're rendering and determines whether, because the UI actually has its own shader, and determines which kind of things it can render as a single pass. And the UI canvas actually supports full three-dimensionality, so objects can be in front and back and layered. And if they're layered, it has to kind of keep them in a certain order. And so if none of the UI elements changes between 2 frames, then it'll actually save all the batching information, and it can render that UI that much faster. The idea is to reduce the number of draw calls used for UI. If you've got multiple canvases, it can't batch information between them because it doesn't know what their spatial relationship is. So the one thing I can think of is that does inhibit the ability to do batching. But if you need to have the canvases at different locations in your scene, that's your requirement. So it doesn't make sense to combine them. Yeah, I don't think there should be any significant performance limitations to having multiple canvases. One of the other thing that's I think I can talk about this. We don't have support for this yet, but in the future, sometime probably later this year, we're going to be adding support for, there's a compositor that happens at the end when the reprojection kicks in. And we can actually, like one of the common things people want to do in VR is have their UI rendered at a different resolution than the rest of the scene. This is a performance consideration. Maybe your UI is going to be much higher resolution. And so there are ways to have the compositor deal with the UI in a separate plane And we're going to be adding support for this. This will probably be part of this new SDK rewrite we're doing internally. But the idea is that I think that'll also improve performance because it'll allow the UI to be composited into the scene at a different level where it's a little bit more efficient and you can get higher resolution. But to answer your question, I'm kind of giving you some additional information, but to answer your question, I don't think there should be any performance overhead of multiple canvases other than whatever limitations it incurs for batching.
Okay, thank you very much.
This may be a little bit more of a general UI canvas question, but would be applicable here as well.
I used to work on the UI team, so I'm set up for this.
There's been a lot of talk here at Build about the Microsoft 365 and being able to richly embed content from across the graph and such. Is there going to be a good way to include one of the custom XAML control as a component in the UI canvas?
I don't know of any plans to do that for custom XAML controls.
Okay.
All right, well, thank you very much.